SwayamPrabha. Digital India. Educated India.
Hello everyone, today is the third lecture of this week. In the last class, we tried to understand the various steps in finite element method through an example. The example we took was relatively simpler in the sense that it had less degrees of freedom such that the manual calculation is feasible. But you know, most of the problem that we come across in real life, they have many degrees of freedom, and dealing with those problems require us computer code. What we will do today is we will write a small program for analysis of Truss using finite element method, and using this program we will see how the larger problem can be analyzed. Now these are the steps involved in finite element method. We have discussed this in detail, but before we start writing the code, I would like to revisit this part, the assembly of element equation based on element connectivity part once again. See, how did we assemble the equations? When we assemble the equations, two important criteria to be satisfied. One is the inter-element compatibility and the inter-element equilibrium equation. We wrote the equilibrium equation separately, and for every equilibrium equation, based on the equation, we populated the stiffness matrices, global stiffness matrix. Now, what we do is we need an algorithm which can be translated into a computer program. Now today, before we write the program, let us see all the steps, the philosophy that equilibrium needs to be satisfied, compatibility needs to be satisfied, and based on that, assembly needs to be done. That philosophy, based on that philosophy, we will see how the assembling can be done relatively simpler way, and such that that process can be adapted into a computer code. Okay. Now, if you recall, these are our element stiffness matrices. The 1, 2, 3, 4, 5, 6 in blue color, they are the global degrees of freedom, and 1, 2, 3 in red color, they indicate the node number. For instance, for element number 1 connected between node number 3 and 1, and the global variables, global degrees of freedom are 1, 5, 6, 1, 2. 5, 6 at node number 3 and 1, 2 at node number 1, and this indicates that this individual column and row, if you see, they correspond to the degrees of freedom, and then this block corresponding to node number 3, this node number 1, again this block gives you the interaction between the forces in node number 1 and the displacement in the node number 3, and this block will give you the interaction of forces at node number 1 and the displacement in forces in node number 3 and displacement in node number 1, like this. Now we will assemble this stiffness matrix now. See, now these are the information that we have. Now first, if you recall, first we initialize the stiffness matrix with, we know in this case that our stiffness matrix is 6 by 6 matrix, and we initialize the matrix with all the 0 elements in the matrix. Then we take each element separately, first element 1, then element 2, and then element 3 separately, and each block we will see in every element, and then based on the block and the connectivity, we will put that information in the global stiffness matrix. How it is to be done? Let's first take element number 1. Element number 1, the first block. The first block we'll take. The first block is between what? First block is between 3 and 3. Now let's see here what we have 3 and 3. We have 3 and then we have 3. So this correspond to this block. So this information will put here. Okay. So, based on this information, we populate the matrix, stiffness matrix. Now, we go to the next block. Next block is this. This is between 1 and 3. 1 is in the column and 3 in the row. So, this is 1 and this is 3. So, these information need to put here. So, we'll put this information here. Now, go to the next block of first element. Now, this element is between 3 and 1. This is 3 and this is 3 and this is 1. So, this is 3 and this is 1. So, this need to be we need to put this here. Similarly, we go to the next block. This is in 1 and 1. So, 1 is here and 1 is here. So, this is 1 and 1. So, based on the information of first element, now we populated the stiffness matrix like this. Now, similar thing we have to do for other element as well. Let's do it for second element. Now, second element will take the first one, first block. Now, this is between 2 and 2. So, 2 is here and 2 is here. So, this information we need to put here. This information is here. Now, go to the next block. Next block is this 1 and 2 and this is 1 and this is 2. So, we have to put this information here. So, this information we put here. Go to the next block. Next block is between 2 and 1. So, this is 2 and this is 1. We need to put this information here. So, we put this information here. And then the last block for element number 2 is between 1 and 1. Now, this is important. 1, 1, 1, 1, 1 we already had in element number 1. And based on the element number 1, these are the entries in this block of global stiffness matrix. Now, what we have to do, this node number 1 is common between element number 2 and element number 1. So, the contribution at node number 1 will come from both the elements. This was the contribution from element number 1. Now, we have to add the contribution of element number 2 to this. So, if we add this to the existing, the contribution from element number 1, then this becomes what? 1 by 4. We have to add 1 by 4 plus 1 by 4. This becomes half. Root 3 by 4 minus root 3 by 4 and root 3 by 4. This becomes 0. Minus root 3 by 4, root 3 by 4 becomes 0 and 3 by 4 plus 3 by 4, this becomes 3 by 2. So, this will be the modified, revised stiffness matrix based on the information of element number 2. Now, let's go to element number 3 then. Element number 3, first we will say 3 and 3. This is, we have 3 and 3. Now, already we have this third node is common between element number 3 and element number 1. So, already this is the contribution from element number 1. Now, the contribution of element number 3 need to be added here. If we add this block to this, this becomes this. Okay. Now, go to the next block. This is between 2 and 3. So, this is 2 and this is 3. So, this block need to be added here. So, this becomes this. Similarly, go to the other block. This becomes 3 and 2, 3 and 2. Now, this information need to put here. So, we put this information here. And final block for element number 3, this is 2, 2. Now, this 2, 2 is this block and this is the information from element number 2. Now, with this information, the contribution from element number 3 need to be added. So, we add this with this and finally, we have this. So, now this is our final stiffness matrix and you will see that this stiffness matrix is exactly same as the stiffness matrix that we obtained in the last class. Now, having said that, the way we have determined the global stiffness matrix here, if you see the underlying philosophy is the same. The compatibility needs to be satisfied and the equilibrium needs to be satisfied. But here what we have done is without explicitly writing those equations, we try to assemble this stiffness matrix. Now, this approach can be adapted in a computer code. This can be, algorithm can be written and that algorithm can be translated into a small program for element assembly. Now, but the basic philosophy is still remains same. The compatibility needs to be satisfied and the equilibrium needs to be satisfied. Okay. Now, with this, let us take this example once again and then write the program. Now, this is the program analysis of 2D class using finite element method. This is written in Scilab. The reason why Scilab is used because it is available, freely available. You can download it and use it. Now, at the very beginning, let me tell you, this is very subjective. The way this code is written, you may write in a different way. But here, idea is not to learn how to write a code. Rather, the idea is to translate all the philosophy, all the steps that we have studied, all the manual calculation that we have done. Everything idea is to translate them into a small program, and then we'll take relatively larger problem and get the solution. Okay. So, what I will do now is the code, the program is written. I will go through the program and then go through the program and explain it, keeping this example in mind. Okay. Now, first is this is the element. This is the structure. We have 3 elements, and these are the coordinates of all the nodes, and these are the forces, and these are the boundary conditions we have. First, we give the node is a variable we defined, and this is the node coordinates of all the nodes. The first node is node number 1. The coordinate will be, if we take the length of each member is 1, the coordinate will be root 3 by 2 0. Then node number 2 coordinate is 1 0, and node number 3 coordinate is 0 0. So this gives you the coordinate of all the nodes. Now once we know the coordinate of all the nodes, now next is how the elements are connected between nodes. That information we need to give. The element connectivity needs to be given. Now the element is another array defined, where the first row of element will give you the connectivity of first element. Second row of the element of this array will give you the connectivity of the second element, and similarly third row will give you the connectivity of third element. Now if we see our problem, the element number 1 is connected between node number 3 and 1, so it is 3 and 1. Element number 2 is connected between 2 and 1, this is 2 and 1, and it is 3 and 2. If you wish that you want to, as we discussed in the last class also, the connectivity, based on the connectivity, the angle needs to be, the orientation need to be given. Okay, so this is your node and element. So now, based on this information, then we can determine what is the total number of node we have, what is the total number of element we have, and then finally what is the total number of degrees of freedom. At every node we have 2 degrees of freedom, and then total number of degrees of freedom will be 2 multiplied with the num node. Num node is a variable which is the total number of node you have in the structure. Now, so this information is based on the nodal connectivity and nodal coordinate and the member connectivity. Next is the member properties or element properties. What are the element properties to be given? Now, material property and the geometric length we do not have to give explicitly now, because coordinates are defined. So based on the coordinates, length of the member can be calculated. Now, member properties, any property can be given. Intentionally I have kept it 1 and 1 because we want to check the results. We want to validate this code, and how to validate it? We have already done the manual calculation for this Truss, and in this manual calculation the forces and the displacements are written in terms of AI, where explicit values of A and AE, explicit values of A and E are not given. That's why it is kept as 1, so that we can validate. We can compare our results and the manual calculation results. Now, next is the boundary condition. What is the boundary condition? Now, BCS is the array which gives you the information about the boundary, and what it tells you that the first this one is the boundary we have, the boundary conditions we have at node number 2 and node number 3. We have boundary condition at node number 2 and node number 3. Now, what boundary? This is the first, every row, the first entry is the node number at which we have the boundary. Now, what are the other 2 entries? Now, then the first entry is, as you see here, the first entry gives you what is the boundary in x direction, and the second entry will give you what is the boundary in y direction. Okay. Now, in this problem, the x direction, there is no boundary condition, there is no constraint given in x direction, only constraint given in y direction. Now, so y direction is, so x direction is written as 1. 1 means there is no constraint, and 0 means there is constraint, right? So, at node number 3, all 2 degrees of freedom, x direction and y direction, both are constant. That's why both are 0. This is the boundary condition we have given. Now, next information is the forces on the structure. The what forces we have? F external is a vector which tells you what are the external forces we have on the structure, and what are the entries. The first entry is the node number at which the external force is there. We have external force at node number 1, so it is node number 1. How much force is there? There is no force in x direction, so x direction component is 0. We have force y direction, it is p. Let's take it is -1. So this is -1. Okay. Now, so this is the external force. Now, all the input, all the information about the problem is now given. All the coordinates, connectivity, then the properties of each member, the load, boundary conditions, all information is given, and that is the end of input. Right? Now, the next step is to calculate element stiffness matrices and then assemble them global stiffness matrix, and then finally solve it. Now, before that, let us initialize the global vectors and matrix and the global stiffness matrix. You recall just now the step I showed you in the global. When we assemble the global stiffness matrix, first we initialize the matrix, all the entries are 0, and then we depending on the we took every element, and then for every element based on the connectivity, we populated the matrix. The same approach will follow here. The first is the initialization of stiffness matrix and the global displacement vector. So, displacement vector, we know the degrees of freedom is now node into 2, because every node you have 2 degrees of freedom, and the size of the stiffness matrix will be the total degrees of freedom. The square matrix, total degrees of freedom will be the size. So, total degrees of freedom. 0 is the column which create a matrix of this size, whatever size you give, and then initialize all the entries and all the elements in the matrix at 0. So, this is the initialization of the vector. Now, this is the F is equal to, this is the initialization of the load vector, global load vector. This is the initialization of global load vector. Now, in the global load vector, we know that there are forces, there are external forces here, these external forces here. So, based on this information, we have to put this information in the global load vector, and this is done here. So, what it is done is, it will read every element in the F external vector, and in the F external vector, based on the information, it will modify this global load vector, keeping all other entries at 0. So, this is the global load vector. Now, we have global load vector, we have initialized the displacement vector, and we have also initialized the stiffness matrix, global stiffness matrix. Now, then once we have the global stiffness matrix, we have to partition these matrices based on the information we know and the information we don't know, right? Based on the known displacement and based on the unknown displacement, that partitioning needs to be done. Okay. Now, this is done here. The boundary condition, these are the ID u comma ID u underscore k. This is essentially the indices of the known degrees of freedom. Okay. Now, for instance, in this case, what are the degrees of freedom are known? In this case, we know that at 2, this was probably U3. U3 is known, which is 0, and then U5 is 0 and U6 is 0. So, 3, 5, 6 are the indices of the known degrees of freedom, and IDUU, these are the indices of the unknown degrees of freedom. And what are the degrees of freedom unknown? U1 unknown, U2 unknown, and U4 unknown. So, So ID U will be 1, 2 and 1, 2 and 3, U3 unknown. So this is based on the boundary condition information, these indices are determined now. Okay. So this will help us when we do this partitioning, when we separate those, when we write this condensed equation, it will help us to do that. These information, these indices will help us to do that. Now, next is the partitioning. Next is the initialization of the partition matrix, like KQ. If you recall the global stiffness matrix, now we have 4 parts based on again known information and unknown information, and KKU and KEU. If you correlate with this discussion in the previous lecture, you will see that these are the same variables we used in the manual calculation. So this is the initialization of those sub matrices. Now this loop is calculating the element stiffness. We don't have to store element stiffness matrix anywhere. In runtime, we calculate the element stiffness matrix, and based on the connectivity, we populate the global stiffness matrix. Okay. Now let's see how it is done. Okay. So the loop has to be done over the entire element. So num LE is the number of element we have in the system. So loop is from 1 to num LE, loop over all the elements. So I1 and J1, see element, if you recall element, this matrix, this array will this array stores the information about the element connectivity. Okay. So first, any particular row in this element, in this array, any particular row will give you the connecting the nodes at the starting end, and the node at the start and node at the end of that particular element. Okay. So say I1 is the starting end and I1 and J1 is the end. For instance, in this case again, for element number 1, starting end is 3 and starting node is 3 and end node is 1. So this will get, this is, so I1 will be 3 and J1 will be 1. Now once we have that, so based on the start end and end end, we can calculate the length of the member. So this is length is calculated, and again based on the, we already know the coordinates of each node, and then based on this information, what is the start node and end node, we can determine the lambda x and lambda y, means the cos, we can determine the alpha orientation of that member or that element, and based on the orientation we calculate what is lambda x and lambda y. Lambda x is cos alpha, cos alpha, and lambda y is sin alpha. Now once we have this lambda x and lambda y, if you recall, the element stiffness matrix can be written in terms of this lambda x and lambda y. So this is the element stiffness matrix. So Ke is the element stiffness matrix. AE, EE, LE, these are the corresponding Young's modulus, length, and area of that particular element. So these will give us the element stiffness matrix. Now here comes the assembling part. This assembling part, if you look at, it is exactly the same thing what we have done just now. Take every element and then take that 2 by 2 small matrices, and based on their connectivity, you populate the global stiffness matrix. So this is done here. So this kg is the global stiffness matrix. The kg will be, this matrix will be this matrix plus the element level information. So if it is done over here, it is 1 by 4 because here it is done every element wise. We have 4 by 4 matrix, element stiffness matrix. So instead of 2 by 2 sub matrices, it is done here. Every entry, every row, and every column in the element stiffness matrix is taken, and then the information is given in the global stiffness matrix. But the idea is same. So this will give you the global stiffness matrix. Now once you have the global stiffness matrix, next is the partitioning the matrix based on known and unknown information. Then this is now where we have, now we start the solution part, the step 5. Now the partitioning is done here. This is this Ku will be the from the global stiffness matrix. This part based on the unknown information, this will give you the Ku, and similarly Ku will be, but from the global stiffness matrix, you scoop out this part based on the unknown and known information. This gives you Ku. Now once we have that, then load vector, already we have load vector also need to be partitioned, means unknown forces and the reactions. known unknown reactions and the known forces. So this is the partitioning of this or the load vector. So now is this solution. Solution is, now once we have this, we have a linear system of equation, and this linear system of equation is solved for unknown displacement. U is the unknown displacement, and this is the lin solve is the command for solving linear system of equation, where Fk is the known force vector and Ku is the portion of this global stiffness matrix associated with this unknown displacement. Now this gives you the unknown displacement. Now once we have the unknown displacement, then the second equation we need to use to calculate the unknown forces, and this is the second equation, which where the information about the displacement we have just now computed to be given and calculate the unknown force. So this will give you the unknown force. Now once we have the unknown force, unknown displacement, again we globalize it. Global displacement vector will be this. We already know in the global stiffness, in the global displacement vector, all the entries are 0 now, but all the entries will not be 0. Now we have determined the unknown displacement. That's information now put in the global displacement vector. So global displacement vector is given. Now the next part in the solution is determination of the member forces, and how we obtain the member forces. If you recall, member forces is obtained. We took the element level equation, and then in the element level equation, we have to only determine the force along the length of the along the axis of the element, along the axis of the member, and that force is a function of the displacement at the nodal at the element level, element coordinate system, and that displacement can be determined from the global displacement through the transformation matrix, and this is done here. Now this is again this needs to be done over every element because all the element we need to determine the forces. Now I1, J1 are again the start and end node of any element. Length is determined. Then this is the lambda x, lambda y, sine and cos theta. And then if you recall, please refer to the discussion in the last class. This was, if you recall, this was your, this is how we obtain the member forces, right? This is the lambda x, lambda y, this transformation, the rho in the transformation matrix associated with this particular displacement field, and UE is the element level displacement. Okay. Now, once we have that, the member forces is determined. Now the solution is done. Next is plotting. Plotting means next is the prosposing. Here there are commands, plotting command, where you can plot all these nodes, all the elements, and then you can plot the deformed shape. You can so this is done here. So this code will be uploaded on the forum. You can go through the code, go through the program, and then compare each step in the program with the manual calculation with the discussion in the previous class. Please note, the idea here is not to develop a finite element code. The idea here is to whatever you have learned, that is translated in a computer program, and this program can be used to handle relatively larger problem. Okay, and this writing a program is subjective. Once you understand how to write this code, how to translate all these calculation, all this step into a program, then you can write on your own. Now, so let's see, compare the results. We need to validate the code. The results we have. So let me open the result. If you recall, these were our displacement, and then these were the support reaction. Okay, so next, so run it. So this is the deformed shape we have, and let's find out what is the displacement vector. So u underscore u will be the displacement. Now this displacement needs to be multiplied by, if you recall, this will give you only the coefficients, This will give you only the coefficient. This needs to be multiplied. These values need to be multiplied with AE, the PL by AE. But we have taken the PLAE all are 1 just to ensure that the coefficients we get and the same coefficient we get from here. Okay. Now then forces, the forces are determined, the forces are like this, and we had, if we calculate the forces here, forces are mm, mm, the reactions are this. Okay. So this is essentially 0, 10 to minus 17 is equal to 0. So these are the reactions, and finally let us find out what are the member forces we had. The member forces we had is the first, these are the member forces we had. Now, if we see, we did not calculate forces in all the member, but at least one member force we calculate. The first member we calculated, this was this 0.577 p, and this is this value. Okay. Now, the positive and negative, it depends on your sign convention. What is your sign convention? In this code, the compression is taken as positive and tension is taken as negative. Okay. So this is the code. Now let's take another problem. Let's take this problem. Now same code. Now this problem has total 6 members and then 4 nodes, and these are the numbering of the member and numbering of the nodes. And then we have forces at node number 1, 5 kilonewton in horizontal direction and 10 kilonewton vertically downward direction. So let's give that input, give that information. So note there are 4 nodes. One is node number 1 is 5, 5. This is node number 1. Node number 2 is 0, 5. So this is node number 2. Node number 3 is 0, 0. This is node number 3, and node number 4 is this is node number 4. Then the element connectivity. Node number 1. Element number 1 is connected between 2 and 1. This is 2 and 1. Element number 2 is connected between 4 and 1, 4 and 1, 4 and 1. Element number then 3 is connected between 3, 4, 3, 4. Element number 4 is connected between 3, 2. Element number 5 is connected between 3 and 1, 3 and 1. Element number 6 is connected between 4 and 2. It is connected between 4 and 2. So this is element level information. And then the member properties given 1, 1, but when you solve a particular problem and depending on the information of that problem, you can give these properties. Now the boundary conditions, what boundary conditions we have at node number 3 and 4, two degrees of all the degrees of freedom are constant. At node number 2, only the vertical, these degrees of freedom constant. Okay, the vertical direction, y direction degrees of freedom is constant. So at node number 2, only y direction is constant. That's why it is 0. X direction, there is no constraint in x direction. That's why it is 1. And then node number 3, we have both the degrees of freedom are constant, and at number 4, again both the degrees of freedom are constant. So this is boundary condition. Then external forces we have at node number 1, and this is x direction, it is 5 kilonewton, and y direction is minus 10 kilonewton. So external forces is x direction, it is 1, and then it is at node number 1, x direction it is 5, and y direction it is minus 10. So this is the only information we need to give. Now then if we solve it, if we just run it, this will be the final solution. Now let's see the results. Let's see the displacement, and if you find the displacement, if you find the displacement is this. Now you may this value you may find this seems to be unnatural, but you please note it is as the coefficient. This needs to be multiplied by PL by AE. Here we have given PL. Here we have given P. L is there, but here it is given P. It is to be multiplied by P by AE. But in this here we have given by A and E. We have given 1. So this needs to be divided by AE. Then you will get the actual displacement. P is also taken into account here. So then support reactions also you can see. You can see the support reaction. If okay, this is this is the support. These are support reactions. You can validate this, and then take one last example. This is the example we have, and this again Now we have total 1, 2, 3, 4, 5, 6, 7, 8, total 11 nodes we have here, and these are the coordinates of all the nodes. And then we have this the member connectivity, member number 1 connectivity. This is member number 1. This is member number 2 connected between 2 and 3, and so on. This member connectivity is given. The boundary conditions. The boundary conditions are, you see, you have it should not be a roller. It is hinge here. So boundary conditions we have here is you have 2 degrees of both degrees of constraint here, and both the degrees of constraint at node number 8. Though it is shown as roller, but it should be hinge. That's how the boundary condition given here. Okay. Now, once the boundary condition is given, next the external forces. External forces we have only here. So at node number 2, we have 10 kilonewton horizontal, vertical direction no force. Node number 3, 10 kilonewton horizontal, vertical direction no force. Node number 4, 10 kilonewton horizontal, vertical direction no force. These are the external forces. And now, if we solve it, you will get a deformed shape like this. So you can calculate the displacement. And here, if you see the displacement, again, these values are very large because this needs to be divided by AE. Okay. Now, so this is how we can write a small program, and the beauty of this method is, see, it is very, and that is one of the reasons behind the success of finite element method, that it can be translated into a computer program. At the end of the day, you will see you are actually dealing with some matrices. Okay. Now, one important point I want to highlight here is, let's take the first example once again. Now, see, Kg, this is the stiffness matrix, right? This is the stiffness matrix. Okay, stiffness matrix. Okay, this is our stiffness matrix. Okay. Anyway, now this stiffness matrix is symmetric. You know that. But then the point, let's invert the entire stiffness matrix. You see, there is a the command is, now if we invert the entire stiffness matrix, you see the command is Now, if we invert this, the problem is singular. Problem is singular means you cannot invert this matrix, right? So determinant of this matrix is 0. So the matrix is singular, but then question is why the matrix is singular. I'm sure that many of you, all of you know this. It has been discussed in structural analysis and the direct stiffness method as well. But I want to highlight this once again because this is very important. You see, when you write an equation, Ku is equal to F, that is the equation we have now. What is that equation? This equation is a representation of our actual structure, right? Now, what happens to the actual structure, that should get reflected in the equation, and what happens to the equation, that is a representation of the manifestation in the real structure. Now we see that when we try to invert the entire stiffness matrix Kg, it says that the problem is singular, the matrix is singular, you cannot invert it. Then what it means? It means that we cannot get the solution. Okay, right. Now see, if we do not, when do we have to invert the entire stiffness matrix? Suppose if we do not provide any constraint, all degrees of freedom are unknown. So we have the global stiffness matrix 6 by 6, and all 6 degrees of freedom are unknown. Then we need to determine the all degrees of freedom without having any constraint. And there we cannot do that because it says the matrix is singular. It means that the structure is not stable. You know, we cannot have all degrees of freedom in a structure. Some degrees of freedom needs to be constrained to make the structure stable. Now, so that is, we know, but at least by intuition we know that. But then same thing is happening here. Our structure, the entire stiffness matrix, the Kg is the representation of the entire structure. Now, the entire structure, all the degrees of freedom, if we provide, then structure will become unstable, and that is manifested here in this error. The problem is, in this warning, the problem is singular. Now, in order to make the structure stable, you have to provide constraint. Now, the question is how many constraints you have to provide. Let us provide one constraint. So, out of this 6 by 6 matrix, we'll scoop out the first 5 rows and 5 columns, assuming that only one constant is provided. Let's see what happened to that. So, inverse of Kg is the global stiffness matrix. First 5 again type of inverse. So, you see it gives you some value, but you see the warning, the matrix is close to singular or badly scaled. This is the so, but still the matrix is not invertible, determinant is almost 0. Again, we know in this structure only one constraint is not sufficient. If we provide two constraints, means first out of 6 by 6 we take first 4 column and first row, first 4 vector, and assuming that last 2 degrees of freedom are constant, and let's see whether it is invertible or not. It is still again the same problem, it is not invertible. So, we provide one more constraint. So, the first last 3, so 3 constraints. So, we have now it is invertible, and this is your invertible matrix. Okay. So, we know by intuition that for this structure, in order to make this structure stable, in order to have a unique solution, we need to provide at least 3 constraints, otherwise the structure will be unstable. Here also we observe the same thing. If we do not provide 3 constraints, then our stiffness matrix, the final stiffness matrix what we use for the solution is unstable. So, this is very important. Whatever you observe in the solution, if your model is right, if your idealization is correct, if your equation closely represent the physical phenomena, then what you observe in the solution, it is a manifestation of some physical process. And what happens to the solution, what happens to the structure, that should get manifested in your solution. If your idealization equations are as close as possible to this to the real structure, and your solution methodology is also correct. Now, there are of course there are some numerical instability, there are some issues there in any method. We'll have a more discussion on that in the last for the 11th week when we talk about various implementation issues. Those things are different. Those things are, some of the problems are purely numerical, but those problems we'll discuss in the subsequent week. But by and large, there is a consistency. There has to be a consistency between the physical behavior and the behavior of the equations that you have in your model. Now, with this, let us stop today. So, next class we'll start the beam and then frame problem, and again we will see similar computer program, and we'll solve few beam and frame problem. There we will have some discussion on convergence and error. With this, thank you. See you in the next class.